Hi, everybody. This is Ian Evans with AWWI, and again, thank you very much for the patience. Welcome to this NWCC webinar on developing technologies for bat detection and deterrence at wind facilities. Before we get started today, I just have a couple of very quick notes on logistics. For sound, you should be able to finally hear us through your computer, and I think a few of you might be on the phone as well. If you're having any technical difficulties with the webinar, please feel free to send me an email at ievans@awwi.org, and I'll troubleshoot as best I can. You can also send us logistics questions through the questions box in the webinar room, and we'll get back to you that way. We'll be doing Q&A sessions after each presentation. If you have a question for the presenters, please enter it in the Q&A box on the bottom right-hand corner of your webinar screen. You can type your question into the dialog box and click Enter or the button at the right to send it to us. You will only be able to see questions you submitted, not those submitted by others, and please feel free to type in questions whenever they come up. And after the presentation, we will read the questions out loud for the presenters to respond. And finally, a reminder that we will be recording portions of today's webinar to post on the NWCC website in the next few days for you to view, along with past webinars we've given. And so turning to today's agenda, the research you'll see presented today is being supported by a recent funding opportunity from the U.S. Department of Energy for technologies to support research to minimize that impacts at wind facilities. To tell you a little bit more about the background for these projects, I'll turn things over to Jocelyn Brown-Saraceno with the U.S. Department of Energy. Jocelyn manages the environmental research portfolio for DOE's Wind and Water Power Technologies Office. And Jocelyn, I'll let you take it from here.
Great. Thanks so much, Ian. So as Ian mentioned, the projects that you're going to hear about today were funded by in part by the Department of Energy's Wind and Water Power Technologies Office. And the WIND program here at the Department of Energy works to increase the viability and sustainable deployment of wind power technologies by working to improve technical performance of wind turbines, lowering cost of wind technologies, and reducing market barriers. And as part of our work here, we have in a part of our efforts to support the sustainable deployment of wind energy, the program has a long history of supporting efforts to evaluate and then minimize the environmental effects of wind energy technologies. In recent years, there's been a growing understanding of the effects of a range of natural and anthropogenic factors on bat populations. And during this time, there's been a growing focus on research aimed at working to understand and evaluate the effects of wind farms on bats, as well as concomitant efforts to develop means to minimize those effects. And this issue is likely to grow in prevalence as a concern for siting and permitting of wind farms as more bat species receive protected status. And to date, research performed by researchers of the Bats and Wind Energy Cooperative and other entities have established that bat mortality at wind farms can be reduced significantly by increasing the cut-in speed of wind turbines during periods of high bat activity. However, while this technique provides a potential option for reducing bat mortality, cut-in speed adjustments also have a negative impact on energy production and thus revenue. And this impact is expected to grow in magnitude as new turbines are designed to operate at lower wind speeds. And so as a result, there's keen interest in seeing the development of of additional methods to reduce the impacts of wind farms on bats. And so the purpose of the funding solicitation that the Department of Energy issued this year was to support the development of bat impact minimization technologies in an effort to provide wind energy stakeholders with tools necessary to minimize wind farm effects and also at the same time to reduce regulatory and financial risks to wind farm developers. The funding opportunity had two major areas of focus. The first was to support early-stage technologies to demonstrate the effectiveness of the minimization technology concept. The second area of focus was on later-stage technologies, and this was really aimed at supporting the testing and demonstration of technologies at operational wind facilities. We made 5 awards out of this solicitation, and you'll hear an overview of each of those 5 projects today. Dr. Chris Hine, who's the Wind Energy Program Director at Bat Conservation International, will speak to their efforts at evaluating the effectiveness of an ultrasonic acoustic deterrent technology. Drs. Amanda Hale and Victoria Bennett from Texas Christian University will speak to their efforts at evaluating the potential for texturizing wind turbine towers to reduce bat mortality. Eric Rickards, the engineering manager from Frontier Wind, will speak about their efforts to develop rotor-mounted ultrasonic bat impact mitigation systems. And this is an effort that is co-funded by the California Energy Commission as well as the Department of Energy. Paul Sievert from the University of Massachusetts Amherst will be talking about their efforts to develop a biomimetic ultrasonic whistle for use as a bat deterrent. And then finally, Kevin Kinsey, engineering manager at GE, will speak about GE's efforts to develop an ultrasonic bat deterrent technology. And before I pass it back to Ian, I'd just like to thank AWWI for organizing this webinar, to the PIs for their willingness to present here, and to you all for joining.
Thank you, Jocelyn. With that, so we can make sure we're catching up to our timeline here, I'm going to turn things over to Dr. Chris Hine from Bat Conservation International, and he will be talking about his project to evaluate the effectiveness of ultrasonic acoustic deterrents in reducing bat fatalities at wind energy facilities. So, Chris, if you want to come off mute, it's all yours.
Thanks, Ian. Good day, everyone. I appreciate the opportunity to talk with you today about our project using ultrasonic acoustic deterrents, and I want to thank the organizers for setting up this webinar. There we go. As many of you know, BCI, through its work with the Bats and Wind Energy Cooperative, has been investigating the use of ultrasonic acoustic deterrents to reduce bat fatalities at wind turbines for nearly a decade. We've worked with several manufacturers, a number of different types of designs over the years, and conducted numerous lab and field studies. In January of this year, at our BWEC science meeting, the committees agreed that deterrent research remained a priority for the cooperative, and we were fortunate enough to receive one of the DOE awards to continue testing this technology. The project that I'll talk about shortly builds on the lessons that we've learned from previous studies and our growing understanding of how bats are interacting with wind turbines. This latter part is very important in how we position and orient the deterrent on the wind turbines in order to influence the area that bats appear to be attracted to or most interested in. Of course, many people over the years have been involved and continue to be involved in this research, but I wanted to introduce the project team for this particular study. From BCI, myself and Michael Schermacher are leading the project and coordinating and managing the biological field work. Iberdrola has been an important partner over the years in BWEC deterrent research, and Stu Webster, prior to leaving Iberdrola, was integral in helping set up this study. Don Rogers and Jerry Ruppy have and will continue to play vital roles going forward. Iberdrola is providing wind energy facility for this study and coordinating logistics for the installation of the deterrents. We are working with renewable NRG systems to manufacture the ultrasonic deterrents for the study. RNRG brings a lot of experience working with the wind industry and with technology exposed on Met towers and on wind turbines. Wally Lafferty and Tom Nostran are leading the engineering efforts for RNRG. And we have the statistical expertise of Manuela Huso from USGS. Manuela has worked on a number of large-scale wind energy and wildlife studies, including our previous deterrent research studies at Locust Ridge. We have a number of objectives for this project. Prior to conducting any test of the deterrents, we wanted to take a step back and spend some time focusing on where and how best to place and orient the devices on the turbines to ensure their safety, compatibility and functionality. And again, we're incorporating what we've learned in the past and taking advantage of recent thermal video footage to determine where bats are mostly interacting with the wind turbines. Our second objective is to assess the performance of the deterrents and how well they interface with the turbine software and our ability to communicate and control the systems. Our third objective is to determine how well the devices perform in reducing bat fatalities compared to control turbines. And finally, we want to compare the effectiveness of these deterrents against a proven impact reduction strategy, commonly referred to as operational minimization, as well as the costs associated with purchasing and installing deterrents versus implementing higher cut-in speeds. So I will run through the general timeline and phases of the study. We're in the process of developing an installation plan. We're exploring options on where to place the devices on the turbines and what type of mounting hardware or infrastructure we can use. And I think we've made a number of improvements over previous tests and how we're going to mount these devices. We're also conducting a number of lab and field tests of the deterrents to better understand the volume of airspace that is influenced by the ultrasonic transmission and how bats are interacting with the devices when they're operating. This winter and spring, we will build enough devices to install on at least 2 wind turbines to conduct what I'm calling a functionality test. This will allow us to run through the installation procedure, test their performance, and identify any gaps in coverage before manufacturing a large number of devices and conducting a large-scale test. It's at this time that we will be using thermal video cameras to monitor bat behavior at treatment and control turbines to see how they're interacting with the devices to identify whether we have any gaps in coverage. After analyzing that data, we'll move on to phase 2 and make any necessary modifications to the device or modifications in how we place or orient them on the turbines. And then we will conduct our fatality monitoring study to test the effectiveness of the devices. And it's at this time that we'll have a number of different treatments, including control turbines, which will not have any deterrents operating, and these turbines will be operating at the manufacturer's cut-in speed. We'll have deterrent-equipped turbines, which will be operating at the manufacturer's cut-in speed. We'll have a set of turbines that are implementing a higher cut-in speed. This higher cut-in speed is yet to be determined, and we're still discussing what the appropriate speed will be for this test. And then finally, we'll have a set of turbines that have both deterrents and will be operating at a higher cut-in speed to see if there's any additional benefit of both of these strategies working together. With that, I'll end my presentation. That's the overview of our project, and I'm happy to answer any questions with my remaining time. Thank you.
Great. Thank you so much, Chris. So we'll take questions for Chris now. If you have any, there should be a box in the bottom right-hand corner of your webinar screen where you can type in your question and send it over to us, and then we'll read it out. All right. Looks like the first one that came in. Question is asking how effectiveness is being measured, Chris.
So the effectiveness will be measured based on the fatality at the different treatment and control turbines. And so we'll be comparing the fatality rate among these different groups to determine how effective the devices are.
Great, thank you. Another question here is, can you describe the actual UAD? What is it? Can you elaborate?
So the ultrasonic acoustic deterrent that we're working with uses transducers to generate sound. The actual specs of the device, the size, number of transducers, and frequency range are still being determined. So I can't completely answer that question, but the main force or transmission that's being produced is through transducers.
Great, thank you. Oh, wow, we've got a lot coming in now. Okay. The next question is, what factors are being considered for determining the optimal cut-in speed for treatment turbines?
Yeah, so we're taking a number of factors into consideration. One is, what's been successful in reducing bat fatalities and is actually being implemented now or maybe implemented in the future through habitat conservation plans or whatever the mechanism is. So, something that is accepted by both the regulatory agencies and from the industry. So something that is being used or might be used in the future.
Great, thank you. All right, another question is, could changes in activity also be used to assess effectiveness?
Yeah, so, while we're doing the fatality monitoring study, we will be monitoring the different treatments with thermal cameras to see if we're keeping bats away from these structures or if we can identify fatalities through collisions that are observed on video. So that will be used as well for the study.
Thanks, and that was actually, I think, answers the next question that had come up, so got two in one there. This question is asking, at what turbine type will you be doing your test phase 1 at, or what rotor diameters do the turbines have?
I think, I'm going to have to check on this, but I believe the blade length is 45 meters. The turbine height, I don't remember offhand. But at some of the sites that we're considering, the turbine types are Gamesas.
Great, thank you. All right. Next question is, if you have problems during the final manufacturing tests, will you simply push everything back? And I'm guessing maybe that means the timeline.
Well, the optimal time to study to conduct this type of study is when bat fatalities are at their highest, which tends to be late summer and fall. So we've hopefully built in enough time on this study to account for delays. And the progress that we're making, I think we're at an accelerated pace, which will give us additional time if anything does come up. So we don't anticipate that being a problem going forward.
Great, thank you. So we've had a lot of questions come in. I'll do a few more, and then we'll save the rest till see if we have any extra time at the end. So this next question is asking, what bat species do you anticipate are present at the site?
So we're looking at sites kind of in the northern latitude of the U.S. So we'll have the 3 tree bats that are commonly encountered, a number of different Myota species, tricolored bats, big brown bats. I think I covered most that'll be encountered at our proposed sites.
All right, thanks. And maybe one more, and
this question is asking, how is this fatality rate measured?
We will conduct fatality searches underneath the turbines in standardized plots, factor in bias trials, searcher efficiency, carcass removal, density weighted proportion to determine the fatality rate at these different treatments.
Great. Well, thank you so much, Chris. A lot of questions have come in that we haven't gotten to yet. If we have time at the end, we'll come back to them. And if we don't have time on the webinar, if the presenters are willing, we will pass them along in writing and try to get responses in writing that we can share with everyone. So with that, we'll turn it over to our next speakers.
Yeah, and so next we will be hearing from Eric Rickards with Frontier Wind about his rotor-mounted ultrasonic bat impact mitigation system. And Eric, we are pulling up your PowerPoint right now.
Looks like the last slide there. There we go. All right. Well, again, thank you all to folks of AWWI and NWCC for hosting and moderating this webinar, and definitely for all of the folks that have dialed in. So we'll go over just a bit of who we are as Frontier Winds, and then our projects, our collaborators, the wind farm that we will be installing at, so the system, and as well as our schedules and objectives, and then give you some updates on our progress that we've seen so far. So in terms of Frontier Winds, we're part of a Halloran Energy Group, which is got a broad experience in operations. There's an owner and operator of over 400 turbines and quite a few more that are currently in development. Also, one of our sister companies is heavily engaged in service, and that's looking at drivetrain inspections. They do blade repair work, and they do a lot of work on the turbine blades in the nacelle and in the hub. And born out of those two companies was Frontier Winds, and we are a technology development company. Our real core competency is in active load mitigation systems, and so that's involving putting sensors and actuators in blades, trying to help the turbines to perform better. So when we saw the solicitation from the Department of Energy as well as from the California Energy Commission, we said this is something that we're relatively familiar with in terms of putting electronics in blades, and that was something that we thought that would be a good fit for us as a company. So that brought us into the project. So our collaborators, we're working with Pattern Energy. They're the owners and operators of the Hatchet Ridge Wind Farm, and they've been gracious enough to help us with access to the turbines, with access to the turbine manufacturer, and give us information about the site. And we're also working with U.S. Forest Service and West Inc. Both that is to develop the fatality monitoring program that we'll be conducting. And we're also working with Dr. Bruce Walker. He's an acoustics specialist that's helping us with the transmitter selection and measurements of the system, both in a lab environment as well as in the field environment. In Frontier Pro Services, they'll be helping us to install the systems at Hatchet Ridge. And this is, as Jocelyn mentioned, this is in conjunction with both the California Energy Commission and the Department of Energy grants, as this project is co-funded by the two grants. As an overview, Hatchet Ridge is located in Northern California, outside of Bernie, which is up by Redding. There are a total of 44 Siemens 93-meter diameter turbines. The cut-in speed is about 4 meters per second, and cut out is at 25 meters per second. So this site is quite diverse. It's ranged. There's quite a change in elevation from about 4,300 feet to 5,400, and it stretches along a ridge line, as you can somewhat see. See along here, the turbines are arranged along the ridge line for about 6.5 miles. So there's not too much in terms of array effects for this one.
Eric, sorry to interrupt you. It's sounding a little bit muffled. I don't know if there's anything you can do to try to make it a little clearer.
Sure, I will just get a little bit closer to the phone.
Okay, thank you very much.
All right. So this slide just shows we've done an initial study on the site with the folks that are site manager, and they've identified out of the 44 turbines, there's 27 here that are labeled that give basically give the searchability of the pad and the area around the turbine. And so they are ranked in order of from A to E, A being the best. So out of the 27 turbines, we would be identifying 26 turbines for both it'd be a 1-to-1 treated turbine to a baseline turbine, so 13 of each. So it'd be arranged on the ridge line there, and that's all being as the fatality monitoring program is being developed by West and the U.S. Forest Service. We have been getting a lot of feedback from Jeff Groover and Ted Weller there, and in developing that plan. So really the motivation for this is Hatchet Ridge is within the path of several species of bats, silver-haired, hoary bats, Brazilian free-tailed, as well as big brown bats. This was found during the 3-year monitoring program after the wind farm was commissioned. And so we're using the baseline study there to get initial fatality estimates, find out what sort of species are there, and that helps us to inform how we're going to be designing the system. Another thing that we can't overlook is that the CEC funding, part of the criteria was that the wind farm needed to be in California. And it doesn't hurt that Frontier Wind we're located in Sacramento, so it's a relatively convenient wind farm for us to be able to access and to be able to do installations. So our system really it leverages a lot of the research that's been conducted over the years past, and showing that ultrasonic systems have shown positive benefits and in deterring bats from structures, and specifically wind turbines. But one of the major drawbacks that has been noted is that atmospheric absorption and just the ultrasonic sound is attenuated, which affects the coverage area. And so what we're focusing on here is a blade-mounted system to mitigate some of these attenuation effects. That way we can get a larger coverage area and try to dissuade the bats from entering the rotor envelope. The system as we have it set up is customizable, and so in particular these bats are their echolocation frequencies are between 20 and 60 kilohertz, so those are the system frequencies that we will be targeting. And the system will be capable of compensating for atmospheric conditions such as humidity and as well as rotor speed. It is designed as a retrofit solution to be installed on the Siemens 93 meter turbines, and we've been working with Hatchet at the Hatchet Ridge site with Pattern Energy and Siemens to maintain the blade warranty. So overall, we're currently in the development phase, which we're estimating to be done in the first quarter of 2016. We'll be installing the system in the second quarter of next year, and targeting a field test and monitoring program in the third quarter of next year to coincide with high bat activity and migration periods. One of the side effects or side benefits of having a jointly funded program is that we're able to use the Department of Energy funds for the first year fatality monitoring, and then the second year fatality monitoring is able to be paid for by the California Energy Commission funds. So during this time, West Inc. will be conducting the searches. There will be daily searches for 8 weeks of each of the treated and untreated turbines, and that's currently some of those details are being worked out as far as the fatality monitoring program, but that is the current overview. So it will happen over a period of two seasons. In terms of our current progress, we've selected a set of transmitters. These are piezoelectric transmitters that are bonded to an aluminum plate, and this is what you see here in the top right is the underside and then the surface of the transmitter, and it's able to it's resistant to weather and some of the environmental effects that we see out on the blades. We've also been able to generate the signals. We're going through multiple sweeps and multiple simultaneous sweeps, and this enables us to keep up the spectral content of the transmissions, and it maximizes the amount of overlap so that we get additive sound, and this helps us to reduce the total number of transmitters as well. Also, because each one of the transmitters, the performance varies, we are also able to equalize the initial signal that's amplified, so we're able to get a more or less flat response. And so what you're seeing here is in the middle is the unequalized and then the equalized signal. These transmitters in our initial testing, we've also done on-axis, off-axis type testing, as well as boundary conditions for mounting. So what you see on the left is the transmitter with a foam surround. It has very different characteristics than a plastic surround, which is more rigidly mounted. You see increased sound pressure levels from a more rigid transmission or transmitter that's more rigidly mounted. And as you'll see here, these plots range from 20 to 60 kilohertz, which is the frequency range of interest. This particular transmitter doesn't show as good of response in the 45 to 60 kilohertz range, so this is something that we're actively working on to improve the transmission from the transmitter. But the one thing that we like about this is we're able to get an upwards of plus and minus 80 degrees, so there's very little directionality to these transmitters, which is very helpful for our coverage of the system.
Eric, just a quick note on time, coming up on the 10 minutes, so if you can wrap up, that'd be great.
Sure. So just really quickly here, we've got our acoustic performance. We've been modeling that. We've also got some feedback from Siemens on where we should be installing these systems so that we don't interfere with the blade and affect the warranty there. Just quickly showing where we're mounting these on the surface of the blade, the trailing edge. And again, these are defined as, from Siemens to help to not interfere with lightning, et cetera, which is something that we'll obviously encounter with these turbines. So the last little bit here is talking about the blade transmitter model and showing what our coverage is. Our targets here, we're trying to hit 65 dB at 20 meters. And so here with a 30 kilohertz signal, we're able to hit those sorts of frequencies or sound pressure levels with the existing transmitters. However, that is based on just one frequency. So if you look at, say, 30 kilohertz, 40 kilohertz, the we're going to be able to achieve that sort of 65 dB threshold. However, at higher frequencies, that's what we're still working on to better the transmitter's performance. So that's where we are currently at, and looking at the next prototype type transmitter and trying to improve on some of the system performance there. So that is the last slide in our presentation. I can open it up to questions at this time.
Great, thank you. We have had some questions come in, but I want to make sure that we've got time to hear from Amanda and Tori, and I know Tori's got to head to class. So if it's okay with you, we'll go straight to their presentation, and then we'll take questions for both of you guys afterwards. So we'll bump these back to back. So Amanda and Tori, are you guys there and ready to go? And I can pull up your PowerPoint.
Yes, we are, Lauren. That'd be great.
Thank you. On its way.
And we're done.
There we go.
All right, thank you. Okay, well, thank you all very much for attending today. It's exciting to see so many people out there who are interested in hearing about our project. What Tori and I are going to focus on specifically is this project, which is texturizing wind turbine towers to reduce bat mortality. Since 2008, our lab at TCU has been working in partnership with NextAir Energy to investigate a wide range of wind wildlife issues that have really allowed us to generate a whole bunch of preliminary data to get to the point where we are now. So for our 10 minutes today, we're really going to start off by sharing some background, providing the rationale for this project, and then we'll talk specifically about our study objectives, which include flight room testing here at TCU, texture coding development, and then hopefully a field test at Wolf Ridge in 2016. And then at the end, we'll share some of our observations from this season.
Hi, so this is Tori. I'm just going to recap on what we do or why we do it, and the reason is why our bats are coming into contact with wind turbines. Now, there are a number of basic hypotheses to do with this reason, and the first one is collisions are random events and just happen because they represent a proportion of the population that happens to be in the area. The second one is that wind facilities and the surrounding areas provide resources for bats, so bats are being brought in by these resources and happen to come into contact with the wind turbines. And the third one is that bats are actually attracted to wind turbines. Now, there are a number of ways bats could be attracted, and it's because they think that the wind turbines provide, or the wind turbines themselves provide a resource, or they misperceive the turbines to provide a resource, or the bats just simply find that turbines are intriguing. Now, all of these hypotheses are not mutually exclusive, so they can, basically any bat can do multiple hypotheses, and they're not species specific, so different species might have different hypotheses applied to them. So we decided to look at the attraction hypothesis and why would turbines provide or appear to provide resources for bats. Now, there are 5 different resources that bats potentially could be coming to the turbines to get, and that's water, food, shelter, mating opportunities, and connectivity. And obviously, Paul Cryan et al. Have done a number of studies that have looked into mating opportunities and roosting opportunities. So we're actually looking at water and food. And so just to recap, why would bats misperceive turbine tower surfaces to be water? Kind of ludicrous. But Greif and Seamers in 2010 actually showed that bats repeatedly attempted to drink from smooth surfaces, demonstrating that they rely on their echolocation to ID water. And they could not effectively distinguish between water and other smooth surfaces. So that got us thinking that turbine tower surfaces are smooth and potentially this applied to them. Now, the other aspect of this is that does the acoustic mirror effect turn turbine towers, excuse the pun, into an effective foraging resource? Essentially, smooth surface makes it easier for prey to detect, bats to detect prey via echolocation, and bats have been shown to take advantage of the acoustic mirror effect on water surfaces and smooth leaves. And as I said, turbine towers are basically smooth surfaces. Bats may be taking advantage of the acoustic mirror effect to glean prey from the towers. Now, for this hypothesis to be true, we have to have one, prey items on the towers, and two, our bats that are essentially aerial hawking bats have to be able to switch their strategy to gleaning. And while there's been a bunch of research by Todd and Walters in 2007 that demonstrates that bats can switch their foraging strategies, it hasn't actually been demonstrated for the species that we find in fatality searches. So that's what we're looking into. And interestingly enough, there is actually condensation on turbine towers, showing that there could potentially be a water resource for them. And a lovely paper by Long et al. In 2010 showed that insects were attracted to the white surfaces of turbine towers and actually congregated on them. And we actually find this at the Wolf Ridge wind farm that we've been doing research at.
Okay, this is Amanda again. And so with some of these observations and points from the literature, back in 2012 and 13, we conducted a series of studies, including night vision behavioral observations at Wolf Ridge, to see exactly how are bats behaving at wind turbine towers and how does this compare to cattle ponds, which is a common source of fresh water in the area. And so using this technology, what we found is that bats would approach wind turbine towers with the same frequency and posture as they did to drink from water sources. They would approach the turbine tower head first with their ventral surface oriented toward the tower, and they would touch the tower either one time or a series of quick touches, appearing to touch it with their heads from these distances. So the table shows the different kinds of activities we saw bats doing in proximity to wind turbine towers, and although the number of potential drinking, those touches of the turbine tower, was quite small, we did see large numbers of passing and close approach to the turbine tower, and passing is associated with bat drinking at water as well. In addition to these touches at wind turbine towers, we are also looking at bat movement within the rotor swept zone and below the rotor swept zone, and what we saw were large numbers of foraging paths, so the zigzagging flight with multiple turning angles by bats in close proximity to the turbine tower, and we also saw a small number of what appeared to be bats going up to the turbine tower and removing an object from that tower surface. So these observations in the field were intriguing, but the scale of a turbine tower and the resolution to see what are these bats doing at the surface, we couldn't quite get in this environment. And so together with the NextEra, we already put in a proposal, and we're developing a bat flight facility here at TCU. And then when this funding opportunity came about from the Department of Energy, we thought it was a great time to take this project to the next level. So working in partnership, again, with NextEra, and then having received the money from the Department of Energy for an early stage technology, our project is really designed to develop a wind turbine tower coating that, one, bats show little or no interest in approaching, and the idea here is that the smaller amount of time bats spend in close proximity to the tower, potentially the less amount of time they're in the rotor swept zone, and that could ultimately decrease their risk of collision. We also wanted to develop a tower coating that could be applied to currently deployed wind turbine towers, so not just in a retrofit scenario, but something that could go out and be applied to turbines today. Another key component is this coating must be economically feasible to produce and apply, and then ultimately contributes to a reduction in bat mortality at utility scale wind facilities. So there are lots of considerations that are going into this turbine tower coating development. Primary among these is that the returning echoes from bat echolocation calls must no longer resemble echoes from smooth surfaces like water. And this must be accomplished using something like a paint additive or an applique at this point in time, so that it could be used to retrofit turbines, although perhaps in the future it could be used at a manufacturing stage. So primarily we want to avoid making these turbines becoming to resemble other resources. So we don't want to make them more tree-like. If bats are indeed misperceiving them to be trees, we might need to consider the grade of the texture and issues of paint integrity and stability over time. We need to include feasibility, and then also the application process. How is it going to go? And so essentially with the flight facility experiments, we used wild-caught bats, and we designed two different types of trials. One was a series of bat foraging trials, and in these we recorded bat activity at a range of surface types, and we are really looking for evidence of gleaning. So could the bats that are being killed at wind facilities in our area, which is north central Texas, do we see this prey foraging strategy switching, and then does prey removal vary with surface types, so between smooth and between textured? And then in the second set of bat behavior trials, we were specifically looking at drinking behavior. So again, we recorded bat activity at a range of surfaces. What evidence do we see of drinking attempts at non-water surfaces? And does this behavior vary with the extent of texture? And so the treatment surfaces that we've included in our experiments include a flat, smooth painted surface that would be similar to a wind turbine tower surface. We also have a wind turbine tower section that's scaled to the curvature of the mid-tower height of an 80-meter tower. We've also included 3 different textured surfaces created with a paint additive that varies with texture grade, and then we also used an applique, so a treatment that could be applied to the top of a smooth surface.
Okay, and the picture you can see now is a picture of our flight facility. Now you can see that there is a mesh between the half of the facility. One side was where we conducted the foraging trials. The other side was the drinking trials. And then the flight facility setup. So again, the water tray is right in the middle. The turbine tower model is on one side. And then we have cameras at right angles from each other looking over these 2 objects so that we can film. There's also another tiny camera. This is a fast-tech camera to get slow imaging of the bats coming down and drinking at the surfaces. So here's what we set up. In order to get distances, we have all of these little marks on the tent so that we can actually see what's going on. And we use pseudocode software to analyze the data. For the foraging trials, we had a massive 537 trials, so that's how many videos my poor graduate student has to watch. So she hasn't got much further, but these are the numbers of bats that actually went through her foraging trials, and she can just about give me a video, which we will play, of bats, eastern red bats, in fact, gleaning.
Sounds like blue mark on the left one. Yellow.
All right. Okay, Lauren, okay, thanks. For the bat drinking behavior trials, we had 77 different trials conducted over the courses of 2 summers. And one thing that you'll get to see in a minute is we were happy that we have 4 of the 6 species that are found in fatality trials and acoustic surveys at wind facilities in this region are included in this. We did see drinking attempts at some of these surfaces. So what we have are data here just for the eastern red and the evening bat, and these both of these species came down and attempted to drink from the smooth painted and the curved surface and the applique, but not from the 3 textures that were based on the paint additives. And then the last couple of slides that we have are going to be just videos, Lauren, if you want to start those, of bats first coming down to drink at the water in the flight facility to give you an idea of our resolution and what we can see. So that's real water. And then this next one is going to be bats coming into a flat painted surface, so a smooth surface. And then the next video is going to be a bat coming into and will touch a smooth curved surface, again with the curvature of a wind turbine tower. So this is just sort of at the start of our analysis from our flight experiments, and currently our progress. We are working to develop a texture coating that will hopefully be applied to wind turbine towers at Wolf Ridge for a 2016 monitoring period. Thank you.
Terrific. Thank you so much. All right, so we'll take a little bit of time for questions, but want to make sure we have plenty of time for the last 2 presentations. So first we'll turn back to you, Eric, and ask a few of the questions that came in. Are you still with us, Eric?
Yeah.
Okay. So we've got, the first question is, how do the transmitters affect the blade aerodynamics?
The transmitters are actually very, very thin, and so we've done some computational fluid dynamics on them, and also since they're located near the trailing edge, the impact on blade performance is minimal. It's barely detectable.
Great, thank you. Next question is, what is your expected per turbine fatality rate as fully operational turbines over the 8 weeks in a year? At fully operational turbines over the 8 weeks in a year.
We'd ideally like to see over a 50% reduction. And again, this is just based on some of the previous surveys and studies that have been done with similar ultrasonic transmitters. So that is our target. Is over that. That also gives us good statistical power to be able to detect that difference within the 2-year period.
Great, thank you. I've got a question about cost. What do you expect the cost to be for the array of the ultrasonic transmitters per turbine blade? And do all 3 blades need an array? And then how many transmitters per blade?
So we're currently targeting 8 transmitters per blade. We're in the process of getting a second and perhaps even a third prototype of the transmitter. So cost is a little difficult to nail down at this point because things are still in flux. But yes, there will need to be an array on each blade. It's largely because the signals attenuate so rapidly. There's not coverage from a single blade. And given the period of rotation of the turbine blades, you're a second or two behind each. The 120 degrees between blades represents about a second to 2 seconds between passes from the next blade. And so there really isn't adequate coverage from one blade's worth of devices.
Great, thank you. All right, and we'll do a few questions for Amanda and Tori. So this first question, I think this came in when you were talking about some of the foundational research you guys did. Was your research during the fall when hoary and silver-haired bats, it seems that for the tower, then you would expect fatalities to be proportional to the bats that are around. Why would migrating bats be more likely?
So these studies were conducted from July through September, which is the peak period of mortality at our site in north central Texas. One reason we are just speculating that migratory bats might be more susceptible is that they could be in areas where they're unfamiliar with local water sources, and when they come down for the day or they leave their day roost to fly off at night, they may be more likely to go to misperceive the surface to be water. We also think that this misperception is going to occur over a very short distance, and so it's highly likely that something else is bringing them into the wind turbines initially. Whether they see this large object on the landscape and they're coming in to investigate it, they might think it's a tree, and then once they're close to the turbine, that's when they would start to get that information from their echolocation that, hey, wait a minute, this appears to be smooth. What is this surface?
Great, thanks. And several similar questions, a lot of props and thanks to you guys for this interesting research. And several of the questions are asking if you have any information or have looked into how the textured surface could affect turbine performance or power generation.
We haven't looked into that yet, but from our collaborators at NextEra, it's not thought that it will affect power generation because this texture surface is only going on the turbine tower and conceivably the nacelle as well, not on the blades themselves.
Okay, great, thank you. All right, well, in the interest of making sure we have enough time for the last 2 presentations, we will turn it over to the next presenter.
Yeah, and now we're going to hear from Dr. Paul Sievert from University of Massachusetts Amherst, and he's going to be discussing a biometric ultrasonic whistle for use as a bat deterrent. So, Paul, if you want to unmute yourself and take it away.
Thanks, Ian. Can you hear me okay?
Yep.
Okay, fantastic. Yes, I'm going to talk about bat whistles today. So, and I'm just going to set up the talk by just saying what probably a lot of us know, and that is that there's estimated to be very large bat mortality across the United States. These are primarily migratory bats, and that appear to be attracted to turbines for a variety of reasons that were mentioned earlier, and they are colliding with the blades. And so we're concerned primarily with migratory bats, which seem to be taking the brunt of the mortality. And we know that ultrasound can act as a deterrent, as a number of folks have already talked about. They've also mentioned that the sound attenuates very quickly in the atmosphere. But we also know that bats avoid noisy environments, noisy ultrasonic sound environments. And we also know that bats can learn to avoid ultrasonic sounds, like moths are known to provide or produce ultrasound to keep bats away from them so that they don't get preyed upon. And some of the research that has been done on ultrasound has tried attaching ultrasonic generators to the nacelle of turbines and producing sound in the 10 to 100 kilohertz range. And there has been some success shown in lab trials, and not as much success when has been demonstrated actually at sites where wind turbines are found. And our proposed solution is to actually develop wind-blown whistles that are producing sound in the 25 to 55 kilohertz range. And these are going to basically be modeled on bat larynxes or voice boxes. And at the left, you see a model. This is actually of the larynx of a ultrasonic calling frog that we are also using as a model. And we want to try to mimic these calls, which can be frequency modulated, meaning that over a very small change in air pressure, they will flip from one frequency to another. And so they are frequency modulated. And here we show a cross-section or longitudinal section through a bat larynx. And basically, in working with some of the engineers at UMass, we're trying to produce a bat whistle that produces sound just by mechanical means. No electricity is needed in this at all, but just the airflow going through these whistles attached to turbine blades drives the sound generation. And this is from a paper which is where folks have shown that basically over very small pressure differences along the one axis, you could get a significant drop in the frequency, and this is the frequency modulation that I talked about earlier. And we'd just like to thank DOE and the other organizations which are helping fund this research. And here's the team, so you can put some faces on this talk. And the engineers working on this project from UMass are Yaya Bonachet and Daniel Carlson are working on the actual whistle designs. Matt Lackner is the faculty member who will work with us on the placement on the blades because he designs blades for turbines. Betsy DeMont is our bat ecologist. Zara Dowling, one of my grad students working with bats, and Michael Smotherman at Texas A&M, who is an authority on bat echolocation and behavior. And this is just to show that we are going to have 5 tasks over the course of the 2-year or 24-month period of this grant. And I'm going to walk you through each of these tasks in a little bit more detail. And the first task is to characterize bat avoidance. And this is being done in Mike Smotherman's lab at Texas A&M, where he has a bat vivarium, and he flies Mexican free-tailed bats and other species, and uses Y-maze, perch selection, and the flight behavior of bats to evaluate whether or not sound is a deterrent or not. And some of the preliminary work has shown that constant ultrasounds bats get very used to, and they just start calling around that constant frequency. And it appears that you need pulsed sounds. So the frequency modulation, I think, is going to be a really critical part of our work. Task number 2 is actually designing these biomimetic prototypes or whistles. And here's the whistle crew up at the top. And we're looking at candidate models being ones from bat larynxes, frog larynxes. And right now, I actually just met with these folks a few minutes before this talk, and they are actually developing the materials that are that show the right elasticity to produce the vibrations and the ultrasound that we need in these whistles. And they will be tested in a wind tunnel here at UMass. Task 3 is to develop a series of prototype whistles over operating over the ranges that are shown in the slide. And we have already done the 3D scanning of the larynx of a greater horseshoe bat, which is shown here. And just as a note that, you know, our whistles are modeled after true bat voice boxes, and we will develop these 3 whistle types, and then we will take these whistles back to Mike Smotherman at Texas A&M, who has, in task number 1, guided us on what frequencies and pulse rates that we need to be producing. We then hand the whistles back to Mike. He runs his, or I should say flies, his bats in the vivarium to see whether the whistles that we have developed are actually acting as a deterrent to those bats. And assuming that we are successful there, we then hand these whistles over to Matt Lackner, who engineers turbine blades, and he will aid us in the placement of these along the edge of the blade to minimize any detrimental effect, if there is any, on energy production by these turbine blades. And as people have mentioned before, the sound attenuates quite rapidly in this high frequency zone, and so they need to be placed along the whole edge of the blade. And then future work that is not going to be done in this 2-year grant, but we hope to actually test the effectiveness of these bat whistles in the field, but that will not be a part of this study, as I said. And then I'd just like to thank all the folks that are a part of the offshore wind energy group that I'm a member of and our team are members of, and they've been very helpful, and I will try to address whatever questions you might have. Thanks.
Great, thank you very much. So a couple questions so far. One is, where will the whistles be mounted and how will it affect the aerodynamics?
It's a good question, and the answer is we don't know at this moment, but Matt Lackner, who is the engineer who will help us with the placement along the edge of those blades, is thinking that they could actually be placed in what they call vortex generators, which actually minimize separation of the air from the blade and can actually should not have any detrimental effect on energy production from those blades. And I'm just trusting him at this moment since I'm an ecologist and he's an engineer.
Great, thank you. One question is asking if the prototype whistles are going to be tested at different temperatures to determine their effectiveness in northern and southern climates alike.
We haven't thought about the temperature issue, but yes, that's a good one. We do not have that in our protocol right now, but that's a very good point, and we might want to consider that also. There are a number of other more pressing priorities with regards to, you know, the different wind speeds that these whistles are going to be meeting, keeping particulate matter out of the whistles so that they are not interfered with. But I think also equally important is this temperature issue, and we just haven't thought about how we're going to test that yet, but I'm sure we will.
Thanks. This person is asking what the minimum wind speed will be that will be needed to engage the whistle.
We're thinking the typical cut-in speed of 6 meters a second.
Great, thanks. And a pretty basic question, how big are the whistles?
Well, we're not actually positive about that either. The ones we are testing, so we have some prototypes right now. We've only started in September, so we are just testing the initial prototypes at this moment. They are just a few inches long right now. whether or not we can get by with something even smaller or whether we'll need something larger for the different frequency ranges remains to be determined. But yeah, so we visualize something in the range of probably 3 to 5 inches long, something like that.
Great, thanks. Any thoughts on how the signal pattern might change when devices are transmitting from moving blades?
No. So we will be evaluating that once we actually, so we have a test wind turbine on a mountain outside of UMass, or a hill, I suppose somebody from the Rockies would say, outside of UMass. We have our own test wind turbine. And we will be putting them on the blades there and then looking at how they function on an actually a rotating blade. But we're hoping that we can predict that in the wind tunnel setting, but there may be parameters that we are not considering on an actual functioning turbine that may be affecting the way that sound is being disseminated, and I think we're just going to have to try them on the real blades to find out if we've overlooked anything.
Okay, thanks. This question is there any concern that these might attract con-specific bats?
Yes, there is a great concern, and right now Mike Smotherman is testing what that pulsed sound needs to be for a bat to actually be deterred or avoid something versus being attracted, because he worries a lot about that. You don't want it to have the opposite effect of actually drawing bats in. His past work has shown basically that there is kind of a reflexive reaction in bats that he flies in the vivarium, and he, when they hear basically the pulsed calls of other bats, which he thinks is just a reflexive reaction so that you basically don't run into other bats and you avoid them. And so we're trying to be sure that we get the pulses right so that they're not attractive versus deterrent.